I hope, did anyone try that? Are you getting the output? The same network, I have given you the values. You just have to build this network and you can simply simulate the network. So whatever, I have done this and I have made the same thing auto tune, and after tuning it, I just got some results. Whatever the results I have obtained, I just copied that block and placed the same values here. I just used the same block, copied that block and placed it here. Now, if you see that this is just almost the same modulation values, but here, if you see that whatever U that I have obtained, that I'm converting into per unit, here I just got the value 0 to 1. In this one, my current requirement is somewhat 1000. If you give that 1000 value, and you may get some larger reference here also, as your reference values are quite large, your U will be somewhat larger value. In this, you have to compare it with U VDC by 2, and you will get the range between 0 to 1. This you can give it to your modulation index, and here I just gave the time, and there is the same two functions. 60, yeah, okay, let it be. So it is 60. You have two functions. It's actually 50. Okay, let it be 60. It's not a problem. So in this, I just compared with a simple reference block. Between two functions, there is only some phase difference, that is pi. If you do that, so I'm switching a basic half bridge inverter, and I'm giving an RL value, the same RL values with a voltage source, and the values of these are given here. Once you trigger this, and you just want to observe whether you are able to attain your required response or not. But in feedback, if you see that for the current, I'm giving the feedback in RMS value. The 1000 ampere, whatever I have mentioned here, is an RMS value. But in this, it doesn't matter whether it is RMS, it is just a step. Here, the same thing, 1000 ampere, it is my RMS value only. But it's like a step, it's just going to get the response. But in this case, I want it to trigger the system. So whatever the response that I have, it is some constant value. In order to compare that, you should have some constant value, which is my RMS value. Okay, this you can compare it, and you can simulate the same. So initially I have given 0 reference. Yeah, if you see that red color line is my initial value, it's going to abruptly increase. I have used plus 600 and minus 600. I mean VDC by 2 at 600. So it is going to oscillate between that. As you can see, it is going to increase a larger value, like it will have 1000 into root 2 times as the maximum value. It is going to reach after some time and it will stay there. You can see it is almost settled and it is oscillating between the same range for the entire time. Okay, this you can try the same. If you want me to place a specific block set, I'll do one thing. This block, as you cannot see this block now, I'll copy this. Control C. I'll place somewhere here. Control V. And you can just, it's like you can keep on trying for 5 minutes, or let us wait for 5 minutes. You just try if you can do that. And then we'll start wind energy conversion systems. So I was just giving these blocks next to next so that you can see that output properly. So this is the actual block set, or if you can see this block itself, yeah, that is fine, right? This is your entire block set. How I am using the block set, see the current response through RMS I have given here, and there's my reference input which is between 0 and 1000. Initially I gave 0 response, then I'll get this response. You can give any switching frequency of your choice. I just gave like some 27 times harmonic content, and I've simulated this. So this is your scope. Yeah, here is your network. You can try for a few minutes. Okay, so you can take some more time. Yes, the mat. Are you saying this MATLAB function? Yeah, same for both means this is the only block I've used now. Where did I use again? Yeah, this one. I just copied that here. And this content also I gave you in chat box here. Whatever the command that was there inside this also I gave it. Like you can see function of I1 y2 equal to sign of m comma t. If you still want to try even more, instead of giving a clock here, you can give a PLL simulation here, any PLL block that you can give it here. If you still want to modify, you can give the theta reference also variation here, and you can observe the response. I'm just telling you the content. I didn't connect the PLL here. You can connect the PLL and you can test the response. And thanks for the questions. It won't wait a while. If we connected our inverter to the grid, how it will track? Since we are giving grid phase and frequency to MATLAB function, here I'm giving grid phase and frequency. Okay, phase and frequency to MATLAB function. So even the inverter generates grid phase frequency. The filters after inverter will displace the generated inverter voltage. Yes, definitely it will be displaced. What? See, you are going to control, you are going to sense that initial values only. You are just assuming that the VT at your part is going to have the fundamental component of that value. And you have to consider that equation also. Between that, you have to use some loop function. If you're going to generate something or inject something, if you just connect it, if you use a PLL, and after detecting it by giving some modulation index, and if you trigger, it is not going to give you a proper output. What you have to do there is you should have some reference, like whether you want a specific current or something. So based on that, it is going to work for that. I think this is what you're expecting. Okay, let us start wind energy conversion systems. So this is part, and when it comes to the last topic, I'm actually covering a very small segment in this wind energy conversion systems, and I'll make a video. Actually, the textbooks that I told you in the last class, in the last session. So among that, I'm going to execute 10.3 and 10.4. For the time being, I'm just going to explain a basic machine modeling of that induction machine. From that, I'm going to realize different things. So with respect to control, I may not do in this session because of the time constraint. That I'll make it at a later stage. And we'll have, today we'll wind it a bit faster because of some constraints in the college. We are being restricted to not to go for more than time. So we're just restricting today a bit fast. And that control video I'll give you on 3rd. Before 3rd, through that NIT Kipli workshop Gmail, only that video alone I'll give that. And the rest of the things, actually I thought of, some people asked me about model predictive control. Some people asked me about lookup table and this wind energy conversion systems. I'm just telling you the basics only. In that wind energy conversion systems control mechanism, lookup table and MPC, if possible, I'll tell that. Even in MPC, I'll not go a very deeper analysis, a very basic analysis I'll go. And in lookup table, I'll tell you how you can use different lookup tables for the same system. The next one is basic control mechanism on wind energy conversion systems, like how you do that in a big bulky system, that I'll tell through that video. This is only for the participants. That too, I will activate that link only for a few days and later on I'll delete that. In the meantime, you can see, if you want, there are so many YouTube downloaders, you can try that. But as I said, it's only for the participants, that too for a few days. Later on, it will be deleted. Okay, when it comes to wind energy systems, first we should know the basic understanding. Among all, then we actually have a lot of machine equations like synchronous machine equation and induction machine equation. Basic of, among all, for all these, the basic reference is DC machine equation. So I'm just going to tell the basic mathematical model of induction machine. If you can understand how the induction machine works, I mean, if you can understand the mathematical model, then you can understand why you have to use flux reference, why you have to use speed reference, why you have to use any reference. But in order to understand that, prior to that, you should able to simulate at least one mathematical model of the induction motion, I mean any electrical machine. So for that, let us enter into the mathematical model of induction machine. If you see that this is a basic equation, like the source current in stator, actually it is for stator and rotor. If you take only the stator, it is RSIS and L phi d phi by dt. Actually it has to be d psi by dt, d lambda by dt. If you represent phi, means it is just a flux, but it has to be flux linkage. It has to be lambda. It has to be lambda like this. I can start annotating now. Actually, the stylus is not working and it is difficult for me to do this. I think the battery of my stylus was over. Let me try once again. I just practiced yesterday. It almost died. No, it's not responding. For the time being, you just understand here itself. I know it's difficult. Okay, just let me try on my touch screen. Where am I there? First I have to choose me, analyst. Okay, to change my role to presenter. think time is consuming faster. And why user is coming. So you can see my screen. Sorry, actually, it's not at all working. Let me try with pen. Okay, but it is difficult to use hand. Okay, anyway, if you see this network, this is a basic equation like V is equal to Ri plus LdI by dt. That means if you just take the equivalent representation of a machine, and if you take the per phase representation, if it is your V, and if you take its inherent resistance Rs something, and if you see the current IABC, then obviously you know V is equal to, if you just take the Vs is you're applying across the inductor. If your Vs is across the inductor, then it is like Ris plus d psi by dt. You can write it as L di by dt, or you can write d lambda by dt. You can write both are fine, because we know that L di by dt is the electrical equivalent representation, or N d phi by dt is a equivalent representation of back EMF. Both are fine if you take that back EMF representation. This is, but it isn't flux representation. It isn't current representation. We won't consider the current representation because again it requires some conversion. So we'll just take the flux, but we'll take what do you call it? Instead of current representation of flux, we'll take flux itself, but we'll take its analogous value in current. That we'll see now. So it's like we have ABC of, let us assume that these are three-phase ABC flux, current and voltage values here. Similarly, let me assume for the rotor, we have these ABC values. See, I have written the model in DQ reference. As I told you earlier, in A, B, C, if you have these three values, this analogous equivalent value here is, it is going to be fixed. This is fixed. This is also fixed. And this is also fixed. Its analogous value in alpha beta is alpha beta. Actually, these lines are fixed, but only their magnitudes is going to change. Like it is going to become 0 and it starts going in the reverse direction. Obviously, it is going to become 0, increase, and later on it's going to come in the reverse direction. Similarly, in alpha beta also, it is going to slowly increase and then it slowly decreases and it starts increasing in the reverse direction. It's at the same place. It is not going to rotate. Similarly, my beta, it's going to slowly increase and it is slowly decrease. But at all the moment in alpha ABC sequence, they will have a phase shift. Suppose if A magnitude is somewhere like this and B is very large, C can be somewhat half of that. So at a moment, these three magnitudes are different, like, but they are displaced by 120 degrees at all the times. Similarly, in alpha beta reference, which are always 90 degrees, at a moment, the alpha can be smaller and beta can be larger. After some time, beta can be smaller, but alpha can be a bit larger. At a moment, beta is 0, whereas my alpha, it will be at its maximum. But if you see that at all the times, their angle between them is 90 degrees. Here, alpha beta magnitudes are changing. If any magnitude is changing, it is difficult for me to apply a PI controller or any control mechanism. If they are stationary, that means whatever the variation with respect to time, that alpha as a function of time and beta as a function of time. Here, ABC also are functions of time. So I just want to remove this time and I want to take its magnitude. You may say that it is something Vm. It is not Vm. It will be like, we'll see now. We'll see its factor. So among all, what we do is we will make some perpendicular vectors, the same representation, which are having a fixed magnitude at all the time. So D and Q, what happens is their magnitude at a moment, it is like this. After some time, they will have a magnitude like this, the dq, but it is going to move vectorially. If I multiply with d omega t, then this d omega t will represent this alpha. But it has to be, if you see that, okay, I'll speed it up 1 minute. 1 minute, sir, I'll speed it up. So if you take alpha and beta, so this is alpha and this is beta. At a moment, the dq axis are like this. This is d, it is q, it is omega t. And if you want to know, if you know d and q, if you want to know alpha, if you want to know alpha, obviously you have to project this alpha here, or you have to project this d here. So you know d, sorry, actually assume that this is your d magnitude. You know d and you want alpha. So, and you know q, take it in opposite direction and project your q here. This is q magnitude. This is q, this is d. But you have to take omega t here, something like d cos omega t, like minus q sin omega t will be your alpha value. Okay. See, if I have a vector like this, alpha and some d, if you want to know the component of d present in alpha, means you have to make its projection, or you can consider this as theta itself. So what is the component of d in alpha is, it is this magnitude. Okay, then what is this magnitude? Obviously you know this as y, and let us assume this as x. Sorry, this is not y, this is root over x square plus y square, or you can take this as c. And if you know this is your x, you want x. What is x? You know theta, you know your y, so x will become your c times of cos theta. Here theta is a varying quantity. So what happens to your x? It is going to vary. What about c? C is not going to vary. So this is how they take theta separately from that. And they will take only the magnitude. For this, as it is a DC quantity, you can apply any controlling mechanism for that. And this is my DQ reference frame. This is my psi Q reference frame, where psi Ls is my self-inductance, M is my mutual inductance. There are different mutual inductances actually, that between stator and rotor, and between stators also. This is called self-inductance. In practical, this is the leakage inductance. Again, this is self-inductance. They will say it is leakage inductance. But in some modelings, this LS, they will consider the inductance between the phases of the same either stator or rotor. So then this LS is different. It is not leakage inductance. It is also a mutual inductance, but it will be called as self-inductance. There are different modelings that a lot of people do. It is not just this model you have to follow. For the same motor, for the same machine, they have their own method of C. We'll see that. We'll see that part now. So this is my DQ reference frame with respect to stator. This is my DQ reference frame with respect to rotor of flux alone. The flux representation is very important in case of wind energy conversion systems because they are electrical machines. Even in case of motor control, the flux estimation is very, very important. For that, we'll take that speed as an analogous representation of flux and the torque as an analogous representation of what do you call it? Torque analogous representation of speed. No, speed analogous representation of flux. This is IQ flux current. The other one is okay. It's like there are two representations in vector control. One is the flux reference. One is the DQ. Stator current reference. So the torque is the speed is analogous to that we'll see later at the time of if there is any phase, then in any other phase of power electronics like this workshop, at the time I'll explain that concept. Now this is like alpha beta reference. If you have ABC sequence, you just have to multiply with this equation. Why there is 2 by 3 means there is only two functions here, alpha and beta, but ABC is 3. If you take the power for 3 phases, it is different, but here you have only 2 phases. Obviously, this 2 power generated by alpha beta should be equal to the power generated by 3 phases. This is one representation. And how do you convert this VDQ? As you see, VDQ is equal to, in terms of alpha beta, it is just multiplication of this function that I already derived earlier. Here I have derived it. Of course, it is clumsy. At the time of explaining the concept, you might know a bit. There is one segment, and if you see that PSI dash, that whatever we have seen here, now this psi RD, psi RQ, and whatever this psi S ABC, psi R ABC dash, which are in differential forms, those we will see here. That is with respect to stator. This is how you see the function. This is because of the mutual flux linkage. There is some flux linkage between the, with respect to that phase, they generally consider one mutual inductance for some people. Some people will consider different mutual inductance for both stator and rotor. So that is what I'm saying. It is up to you how you choose that. And it is your Q axis. There is just one equation. Similarly, you will get for D. Similarly, you will take for rotor. Here I have taken 0. If you consider a simple squirrel cage machine, so your rotors are slotted, your rotor slots are shorted, and so your ABC will be V rotor ABC will become 0. But if you take a doubly fed induction machine, these values are non-zero values. If you take a doubly fed induction machine, and what is your XML? Some values XML that we'll see. And here is your flux representation, current representations of all the phases that I have just mentioned. And your torque, this is very important. This torque is actually IQS side ES and side ES IQS. Remember, assume that this is some constant. Ignore that. This is your base speed. Here, what they do in a vector control, what they do is they will make one term 0 and they will just use this term alone to get the required speed. If how we can make this term, why you want to make this term 0 means, then the torque is actually a direct proportional equivalent of these two, and it is easy for you to control the torque. So this is one segment. And if you see alpha beta representation of that and ABC equivalent, why we need again ABC means obviously we have given ABC currents. Now we need to do inverse transformation, inverse Bach and inverse Clark transformations to get the required currents. We need ABC currents, right? We have three currents. That currents we need to find. So using these equations, you can do that. There is something called model 2 in, as I said earlier, here you have some flux representations. The same flux representations, here it's like they will consider some mutual inductance of like leakage representation like this. But in model 2, what I consider is I'll consider this sigma. Sigma is actually Lm square minus Ls Lr. Lm square minus Ls Lr by Lm. I think this is the one. Yeah, Lm square. So this is your sigma. So you think it's over root, I think probably. So root you may get it. So by substituting the sigma and see that representation, this representation is again different. I'm taking this is again a modified version of the same. Here you are taking that if you take omega e here, then it is stationary reference frame. If you take omega e minus omega r, then it is rotor reference frame. And if you take omega e minus omega e, that means if you take it as 0, then it is called zero reference frame. Sorry, it is called stationary reference frame. Sorry, synchronous reference frame, stationary reference frame, and rotor reference frame. There will be three references based on whether your omega e minus omega r 0 value or omega e value or omega e minus omega r value. Your system is going to behave in each pattern. There are different controlling methods in vector control based on your representation, like whether you are considering your model in rotor reference frame, that does matters at the time of control. If you're making in rotor reference frame, your control mechanism will change. The reference fluxes, they will change. If you take stationary reference frame, it again will be changed. So it is up to you how you choose that. And it's the same thing here, it is with respect to stator, the same with respect to rotor in a different model. Okay, let us simulate this first. Obviously we know whatever the reference frame it is, here it's like the reference frame is different. Whatever the reference frame, here it is synchronous reference frame. In this omega e minus omega, obviously the rotor, the EMF generated will be uh, the air gap flux to rotor speed. That is why the rotor currents are a bit less compared to stator currents. If rotor currents are also rotating at synchronous frame means your stator current, then it may make in alignment with your rotor stator air gap flux, and obviously the current will be 0. If the current is 0 means there won't be any I mean what you call the air gap flux and your rotor positions are at same alignment, then there won't be any rate of change of flux, then it becomes 0. Actually I was going in a different directions. It is okay, let's go to simulation first, then we'll understand the concept now. Okay, 1 minute. I think I'm taking too much time. Okay, as I said, for the time being, we'll just simulate this induction machine. Then we'll go for what you call. We'll go for that video, that control of induction machine. How I'm going to explain that, it almost takes 40 to 50 minutes for me to explain the control mechanism. Okay. Let me add that here. Okay, that was not there. Do it in this laptop itself. I think I'm confusing you. Yeah, I can understand because the concept is difficult for me to explain in this short time. As I said, I'll make the proper thing at a later stage, but this is exclusively for few days. That is exclusively for you. And don't share it, okay? If you can understand, you make it on your own. Whatever your understanding is there, that you can share it. 1 minute, let me open the MATLAB application. Not there. Just a minute. Today's session was not proper actually. The time consumes very fast. MATLAB drive. Change rule, make presenter. 1 minute, let me share the MATLAB application also. Just 1 minute. It's almost there. Okay. Share application. Bit faster. I think you can see the MATLAB screen. So I have three phases. So ABC phases are there. These phases I'm just taking it. It is the basic machine modeling. If you can do this, I can tell you, if you can understand this mechanism, I can tell you, then you can build your own controller. You need the state space representation. I mean, you will get that state function from this. And some people, there is something called the latest nonlinear methods that are coming. They don't consider whether you are connecting an induction machine or whatever it is. You can do the control irrespective of that, but you have to sense a few parameters like currents and voltages. Some people said like deep learning. Yes, you can do that. Okay, for the time being, as I said, I'm just converting my ABC sequence to alpha DQ sequence. Here I've just used an existing three-phase PLL. As I said, this is somewhat better. You can use 50. That is also fine. You can use anything here. That's not a problem. Apply. Okay. You can take the screenshots of this. First, you can take its screenshot for this one. So it's the voltage sources is up to you. Whatever you want that you can take. Then my ABC sequence. So I've used some function block. There is something called FCN. Not FCN. MATLAB function. So there is something called function. Yeah, this math function. Not this math function. Okay, you can see here itself. If you type FCN also, it will come. Okay, ignore that. So there is some block called function. You can directly type the equation that whatever you have. Here I have my three equations that I'm directly giving it to this. Using that, as I said earlier in this, so in this one, as you can see, ABC sequence. ABC sequence. Okay, yeah. As we can see, ABC sequence. In this ABC sequence, we can we can convert it to DQ conversion. So that DQ conversion values I told you here. So you have to first convert ABC to alpha beta representation, and from alpha beta to DQ you are going to convert. This theta, every time you have to predict that. To predict that theta, you have to use a PLL there. And as you can see, I've just written this equation 2 by 3 for alpha conversion 1.5 and minus 0.5. This is what I just written. It's actually minus 0.5. I forgot to write. It's a it's it's minus 0.5 here. Similarly, there is another equation of like root 3 by 2 and minus root 3 by 2 0. I didn't even consider this here because I don't want the ground value as I'm considering a balanced one. So just consider only 2. Here I'll get ABC and I just got alpha beta here. Through PLL, I have given it as an input. From here again, the same thing. If you know theta, you'll simply multiply cos theta, and you know V alpha that you have obtained from here. This is your V alpha. This is your V beta. Here I'm giving theta as external. So I'm again writing a function U of 1 like this. There is something called math function, I think. Math function. This. See that. Okay. So this is the function blocks that I have created. FCN only, but it is not coming. Okay, let me type enter. That means it will choose transfer function. This is different. Actually, this model was created in 2018 B for me, and this is madam's laptop. So it is in 2020, 2021 B, 2021 A. I don't know something. Okay, irrespective of that, it is like ABC to DQ conversions we have done here, and that DQ you can take it screenshot, and these function blocks you can try to implement this. As I said, you have to use a minus here. Pen, it has to be minus. I'll save this. So you can go for that induction motor. For the time here, actually, if it is a motor, you can give a load torque 0. But here TL, you have to give, I mean, if it is a motor, its torque value 0. But in case of induction machine as a generator, you have to give some load value here. Without that, it's not going to operate. You can say that it is a machine instead. I'll tell you what's the difference. So here you get VDC, VDQ. Now all the calculations will come here. So the flux calculations, as you can see, here we have done that flux calculations. These are the flux calculations. This is the differential form, and the same, it is a function of itself. That means there has to be a closed loop. Similarly for stator and rotor, there will be 4 functions. Flux like this is for rotor and this is for stator. If you just go there, I've just used an integrator and I've took back the function and I've just multiplied. Whatever the equation I have written, the same equation I have mentioned. Here omega b, why I'm multiplying, here is there is something called unit factor representation. For that, I just converted this into per unit because these values are normal actually. So I just converted into per unit, and later on I multiplied the same thing with omega b. So you can see that. So it is my FDU, and FMQ calculation is again different, that we'll see now. So like this, we will find FDS, FQS, all these values, and we'll give it to that machine. Here now, actually from this, if you can see the flux value, these are the flux values, and there are some current values. We know if you know the flux values, you know how to find the current values. So from the flux, ABC to D, not this. Somewhere I missed. Yeah, here you have calculated the flux values which are in closed loop. Like you're going to take its feedback and you're doing its model. From flux, we're going to calculate the current. Like the same formulas that I have here, like IDS, IQS. Some people will not accept this form. They will use their own form. Even that variation of selection will affect your control mechanism. So you have that function, and you can calculate IQS and IQR, like IQS and IQR. Similarly, you can calculate IDS and IQR. You can take its photo. All these blocks, you can take the screenshot of them. Once you find the currents, this FMD is again FMD is again a function of that. FMD and FMQ are again a function of fluxes. So again, this fluxes are function of FMD. See, from this FMD and FMQ, whatever the fluxes that I have obtained, you have seen that this FMQ and FMD that I actually took back and I have calculated these fluxes. These are interrelated. From this, as you know, the fluxes of all these things, you can find the torque. The torque equivalent is here. So you just have to separate the torque. For the time being, I just consider this load torque as 0. And this is my representation. Once you get the torque, this is electromagnetic torque. Using this equation, I found that electromagnetic torque. Once you get the torque, you simply have to subtract that with the load torque, and this is your inertia and all these mechanisms. See, there is something called, suppose you have a random machine, maybe it is a motor or something. There is something called system identification. Whatever suppose these are all, if you observe that, whatever the equations that I have here, these are all state space representations. Even you have to find the state space representations for current. That means you have to simply alter few lines, then you will get for currents also. Even for the fluxes, everything. So that state space representation, whatever the thing that you have got here, I was explaining some concept. Okay. If you have all this, and you operate your machine for a given voltage and at a given speed, you don't know the parameters of RS, XLS. There is some concept called system identification. So what you do is you give a state variable format to that, and you use optimization techniques to find its values. Okay. And these values will be more accurate so that your vector control will properly work. If you use open test, what do you call open circuit test and short circuit test, you may get this RXL, but they are not as accurate as the system if you do that for system identification. So system identification is somewhat important. That will give you a proper values of all these values like RS, everything. So once you get all this, I have got in DQ format, but I need it in ABC format. I think it's just an inverse conversion. Whatever the things that I have mentioned here, if you have DQ conversion, If you have DQ again, you know DQ, you have to convert into alpha beta. Once you all know alpha beta, you have to convert into ABC. That is just these equations alone. I have mentioned it here as a matrix form. Once you do that, obviously by some factors, I just made some factors to see the values properly. You can simulate this. I have plotted the characteristics of torque to speed ratio. So how my torque is varying with respect to speed, that you can see. If it reaches the synchronous speed, obviously you know what the torque will become. It has to become 0 because there won't be flux, rate of change of flux. Obviously, if the flux rate of change is not available, your torque will become 0. So this is how we can operate it. If you want to say that, so initially, as you know, the starting current is very large. Even you have to adopt few things in your control mechanism to reduce the starting current also. Even that can be done. Some people, what they do is some vector control mechanisms, they don't have what do you call? Some vector control mechanisms, they don't have the inherent property to reduce the starting current. So what they use is for some time they will use V by F control, and using V by F, it is easy for them to reduce the starting current. Once they reach the steady state, then they will move to vector control. So even that mechanism is also fine. You can use that. So this is how we can do the simulations. I want you to take the screenshots of this. This functions, just one I have opened, you can see that. So we'll start a validatory session in few minutes. As I said, I'll share you that video by 3rd August. Okay, go back. I think this is fine for you. Now you can take the screenshots of this. First take its screenshot, then I'll go one after the other. So this is the first block again. Now in this, the first block, it's actually, you don't need to see if you can write these equations. I have written all these equations in sequence only. Based on these equations, whatever the pattern that I have written, these equations only you can build there itself. So instead of making that, you can take the screenshots of these equations and you can try the same. This first one, you can press Windows print screen. If you take Windows print screen, then it will be saved directly. You don't need to copy and paste it in Word. If you press Windows and print screen, then it will save it in some place that you can search it in Google itself. Where you can find, mostly it will be in document, or some places it will be in picture screenshots. So this is second page. You can press Windows screen. Third page, fourth page. You can see the numbers. Actually, we have page numbers here. 12. Next one. Next one. And next one. Okay, this is the last one. As I said, you have the modeling here. When you can write your equation in state space format, then you can do whatever the control that you want. As we have seen that how we have a nonlinear system equation. Suppose here see, there is some product. So you can try a Jacobian matrix representation here. Everyone, it is not mandatory that you have to go for vector control or director control. Vector control means DQ reference. Director control means alpha beta reference. They don't consider again PLL and all. So it's a hectic for them. So it's like it's one is ABB, one is Siemens. So it's up to you how you choose that. You don't need to follow both of them. You create your own controller, but make sure that you identify these elements properly. I'm talking with respect to hardware and software both. So there is one representation. Just give me a minute. In the meanwhile, you can see this screenshots. You can take it screenshots. Okay, it seems like the coordinate is so number 12 you want. Yes, this is number 12, sir. There was some issue happening in the college and the coordinators went there to solve that. So I thought of winding the session now and even I have to go there. If I just want you to share your feedback, whatever the suggestions that you want or anything that you can share it now. I'll make all the participants unmute. And any suggestions, it's not like whether if you hate something, then you can share it. If you like something, then you just keep it. Select all. I'm making everyone unmute. Share their feedback, they can share it. Of course, this wind energy consumption systems is very basic. I'll give you a link on that video, as I said. Thank you, but thank you, sir. Any suggestions, sir? Shivam Bharti, sir. So the session recording that actually the coordinates have to decide. The session recordings will take time to upload in. We won't give that. We won't upload that in YouTube. We will share you the links directly to you once the corporate filing is done. Okay. It will take a maximum of 1 month, something like that. So we are actually claiming for both this phase and the previous MATLAB sessions. Then we'll give it to you. Hello, sir. Good evening, sir. Thank you, sir. But I want some suggestions. I mean, have you felt that, and what are your expectations? What you actually get here? So most probably with respect to me, some sessions on hardware can be done. Sir, in order to implement hardware, suppose if I'm using a microcontroller, you should know about the registers, everything, pin diagram, registers, everything. To explain that itself, I need 7 days. There are some interrupts, registers, pin diagrams, and how the memory that it has, everything. To explain that itself, I need 7 days. And hardly in that 7 days, I can explain a basic PWM method or basic SPWM using MATLAB. That is the only thing I can do. It's not that easy to directly deploy that. We'll see, sir. We'll try to make somewhat relevant. I mean, we'll try to make some hardware session in the next phase if possible. Suggestions.
डिवाइडेड बाई 5।
What is missing?
भाई
I
50
just,
लाख में बिल्कुल से कमी
it's
नहीं है,
like,
पूरा 100
as I
किलोवाट
said,
कम
na,
हो जाएगा, बिल्कुल
I
कम
told you it earlier
बोल
itself.
रहा हूँ। ये तो छोड़ो, वो बताओ ये कितना
There is something OBS Studio.
बड़ी चीज कमी उतनी होनी चाहिए इंसान में। हाँ तो तुम एक